took before in the previous video that the electric field just outside the surface of a conductor, when the conductor is in electrostatic equilibrium, the electric field has to be normal to the surface. So this is kind of a pictorial view of what the electric field just outside the conductor has to look like. Now the question in this video we want to ask is, can we actually find the value of this electric field? For instance, at this location or at this location. At any location just outside the conductor, can we find an expression for the electric field? So we can do that by taking a Gaussian cylinder, very small cylinder. I just drew it big here so you can see it, but it's a very small cylinder. This height tends to 0, and also the size of this face tends to 0. And part of the cylinder is outside the conductor, this blue part, and then the part that's dotted here is inside the conductor. So basically the cylinder is puncturing the conductor. It's perpendicular to the surface at that location, and it goes, half of it is inside the conductor and half of it is outside. If you look at the electric field, we said the electric field has to be perpendicular to the surface. That means on the side surface of this cylinder, the part that's outside, the direction of the electric field and the direction of the area vectors will be 90 degrees. So the flux through the sides here outside will be 0. Now on the face, the top face of the cylinder here, the electric field, as we said, it's perpendicular to the surface. So it's pointing perpendicular to this face. And the area vector for this face is also perpendicular to the surface, and it's in the same direction exactly as the electric field. So the dot product between E and dA becomes just EdA. Then anywhere inside the surface, anywhere inside the conductor, the electric field is 0. So there's no electric flux at all. When we come to apply Gauss's law for this cylinder that's partially outside and partially inside, integration of E dot dA, we can cut it up into 3 parts. The top part through this face, and then the sides on the outside here, and then the part that's inside the conductor. For the top part, we just said that the electric field and area vectors are in the same direction, so E dot dA becomes EdA, and then we said that we are going to make this cylinder face very, very small. So if you get the electric field here, or here, or here, anywhere on the cylinder face, when the size shrinks to 0, the electric field has pretty much the same value. So we can take E outside of the integration. And then integration of dA is just the area. So the left-hand side, this whole term just becomes E times the area. The electric field at that location where we made the cylinder times the area. Okay, for the sides, we said that the angle is 90 degrees between the electric field and area, so the flux is 0. So this term is 0. When you're inside the conductor, the electric field is 0 anyway, so integration of E dot dA is 0 also. The only term that survives is just E times A. So this part, left-hand side of Gauss's law, just turns out to be E times A. Okay, what is the charge inside the Gaussian surface? Where is the charge located? Remember we said that the charge has to be located on the surface. So the only place where there's charge inside this cylinder is in the intersection of the cylinder with the surface of the conductor. And the intersection will be in the shape of a circle, small circle. And how can we write down the total charge on this small circle? We can say that the charge on the circle, it's a surface. We can say it's the sigma, the charge per unit area, times the area. And why do I call this sigma local? Because the charge per unit area here doesn't necessarily have to be the same as the charge per unit area on different places on the conductor. So that's why I'm going to label this as sigma local. It's the charge per unit area at that location where I want to find the electric field. So let's look at Gauss's law then. The left-hand side gives me E times A. The right-hand side gives me sigma local times A over epsilon naught. The A and the A will cancel. And so you get the result that the electric field is equal to sigma local over epsilon naught. This is the normal component of the electric field. just outside the conductor. It equals to the local charge per unit area divided by epsilon naught. So just to recap this part, remember I said that the sigma local doesn't have to be the same at different places on a conductor. In fact, we'll show later on that sigma local is much higher when there are sharp edges, and it's much lower when there are curved, smooth edges. So if sigma local is higher at sharp edges, then also the electric field will be larger at sharp edges. And so this is basically kind of a cartoon picture of what the charge looks like on the surface of the conductor and the electric field. And if you want the value of the electric field here, then you need to know what sigma local is over here. If you want to get the electric field here, just outside the conductor, then you need to know what sigma local is over here, right at that location. So we're relating here the electric field, the normal component of the electric field just outside the conductor, to the local charge per unit area just below it on the surface of the conductor. So even though the normal component of electric field inside the conductor is 0, we just showed that the normal component of the electric field just outside the conductor is not 0. So there's a mismatch between the electric field, the normal component inside the conductor and outside. And the reason for this mismatch is because of the presence of charge on the surface of the conductor. This is very unlike the case of the tangential component, which we showed was the same as the tangential component inside the conductor, and so was 0. So the normal component of the electric field just outside the conductor is not 0 in general if there's charge located on the surface.